All right, AP Chemistry, Hoover High School. This is just an opportunity to read the notes for the winter assignment. It's been posted. You do not need to do this video, but this is a chance if you want help with some of the pronunciation or what some of the concepts mean. I'm just going to read the notes that I gave you for the winter assignment, and you can do that along with me. All right, so it's about 15 pages, but a lot of images and graphs and things like that in. All right, so what we're dealing with is atomic structure. This is a standalone subject, meaning that if you had not been in this class up until now, you could learn this. It's not something that requires you to know anything about stoichiometry or balancing equations or anything else. It's really a subject of physics, but they included it in AP Chemistry because there are concepts that you need to know to do other parts of AP Chemistry. Okay, so let's go ahead and get started with this. So first we're going to start off with a topic that you had in physics about waves, and particularly electromagnetic waves. So, all right, so electromagnetic waves. Understanding electromagnetic waves and light is necessary to understand how energy is transferred into and out of an atom. Visible light is one kind of electromagnetic wave. All of the energy we receive from the sun is in the form of electromagnetic waves. So that includes light, heat, and a lot of types of radiation that are very bad for us, but fortunately are deflected away by the Earth's magnetic shield. A transverse wave moves in a roller coaster fashion. So you see that up and down, that kind of roller coaster fashion is the way a transverse wave moves. It literally moves through space like that, up and down as it travels through space. The top of the wave is called a crest and the bottom a trough. The distance from a point on one wave to the identical point on the next wave over is called a wavelength. So you see that on the graph. It's the straight line distance. Usually we talk about crest to crest, but it could be any point to the identical point on the next wave. So it's a straight line distance, and it's a measurement of length. So it's measured in meters, micrometers, nanometers, something like that, some measure of distance. It's called a wavelength, usually measured from crest to crest. A cycle is one movement of a wave, for example, from one crest to the next. So a cycle would be if you're on the top of one of those crests and you went down and came back up to the next one, that's a cycle. So it's not the same as a wavelength. A cycle is just a number. It's how many times you go down and come back up, go down and come back up. Whereas a wavelength is a straight line distance. As I say, it's measured in meters or micrometers or nanometers, and that's a straight line distance between two crests. All right, so a cycle is one movement of the wave, for example, from one crest to the next. A wavelength is the straight line distance between crests. A cycle is one complete down and up movement between crests. Visible light has properties of both continuous waves and particles. So we're going to talk about that. So first we're going to talk about the wave properties of light. And this is a subject that you dealt with if you've had physics. You've talked about waves and how light is a wave. So frequency, and it uses this Greek letter nu. It looks like a combination of a V and a U. It's pronounced nu, and that's the symbol for frequency. Now, if you remember back to your physics class, you used a lowercase f for frequency. So they've changed the symbol on you, so you just have to kind of be aware of that. So frequency, nu, pronounced nu, is how many cycles pass a point each second. The units of measure for frequency are cycles per second. It can also be expressed as 1 over seconds, seconds to the negative first power, which is 1 over seconds, or the most common is called a hertz, and it's just abbreviated Hz. So that's the unit of measure for frequency. Again, it's how many cycles pass a point each second. Period is the time it takes for one cycle to pass a point. A period, and the abbreviation for period is T, is measured in seconds. In figure 3 below, SpongeBob is standing above crest 0 when his watch reads 0 seconds. So let me just scroll ahead to that on the next page. So here in this box we explain the entire concept. So cycle is one movement through a wave. If SpongeBob slides down from crest 0 and back up to crest 1, that's one cycle. Frequency is the number of cycles that pass SpongeBob each second. So SpongeBob is standing still. The wave is moving, and it's moving from your left to your right. So it says direction of the wave to the right. And period is the amount of time it takes one cycle to pass SpongeBob. So if you look at this, this is kind of a before and after picture. The before picture is above. At 0 seconds on SpongeBob's watch, he's standing above a crest that we'll label crest 0. And you can see there's crest 1, crest 2, crest 3, crest 4. 1 second later, the wave has moved to the right. So now SpongeBob is exactly where he was. He's even with that dashed line. But now crest 4 is below him. That means 4 cycles have passed him in 1 second. So it took 1 second for that to happen. So the frequency is 4 cycles per 1 second, or 4 cycles per second, or 4 hertz. So that's a frequency of 4 hertz. Now what a period is, it just asks the reverse question. If 4 cycles pass in 1 second, how many seconds does it take for 1 cycle to pass? And the answer would be 1/4 of a second. So as you can see, from crest 0 to crest 1 would be 1/4 of a second. Crest 1 to crest 2 would be another 1/4. 2 to 3 is another 1/4. And 3 to 4 is another 1/4. That's a total of 1 second for the 4 cycles to happen. Remember, it's not how many crests passed him, it's how many cycles past him. So it's from one cycle, one crest to the next. And that's called the period. And the period is simply the reciprocal of the frequency. So if the frequency is 4, then the period is 1/4. So at 0 seconds, crest 0 is below SpongeBob. 1 second later, crest 4 is below SpongeBob. This means 4 cycles have passed in 1 second, which is a frequency of 4 hertz. The period is 1/4 second because this is the time it takes 1 cycle to pass SpongeBob. Okay, so we'll return up to the text now. So it says in figure 3 below, SpongeBob is standing above crest 0 when his watch reads 0 seconds. 1 second later, the wave has moved to his right, to your right actually, and he is standing above crest 4. This means that 4 cycles have passed in 1 second for a frequency of 4 hertz. It also means that each cycle took 1/4 of a second, which is the period of the wave. A transverse wave describes the shape of a wave as an up and down wave, such as you can create with a spring or a rope. Maybe you did that in physics. You went outside with a rope or spring and you just shook it up and down, and it formed this type of wave, this up and down type of wave. Electromagnetic waves have an electric part and a magnetic part that travel together at right angles. So if you see that image there on the right, the electric part is the up and down part, the magnetic part is the side to side part. Now that could be reversed. We're just arbitrarily saying that the electric part is the up and down part. It could be turned in any angle actually, but they're at 90 degrees to each other, as you can see. So electric waves and magnetic waves travel together in what's called an electromagnetic wave. Energy from atoms comes in the form of electromagnetic waves. So you may remember that we said that the type of energy, when we talk about energy in chemistry, we're talking about heat or enthalpy, if you remember back to thermochemistry. And that's true for chemistry, but this really isn't chemistry. This is really quantum theory or atomic theory. It's more in line with physics. So the kind of energy we're talking about in this unit is electromagnetic waves. Generally, though, in chemistry, when we talk energy, we're talking about heat energy going into or out of a chemical reaction. No chemical reactions involved in this unit, though. We're talking strictly about how atoms work. Okay, light is one of many types of electromagnetic waves. All of the energy the Earth receives from the Sun is in the form of electromagnetic waves. Figure 4 on page 13 shows the electromagnetic spectrum, which displays all types of electromagnetic waves. Okay, so let's take a look at that. That's something you should be familiar with. I kind of left it at the end. You can reference that throughout this unit. Here it is, and I'm going to shrink it down a little bit here. Okay, there we go. All right, so let's take a look at this. This is the electromagnetic spectrum. These are all the different types of electromagnetic waves, and really there's not a strict distinction between one type and another, between visible light and infrared and ultraviolet. It's a continuum, and this is called a continuous spectrum. Over on the left you have the shortest wavelength and the highest frequency, and that would be gamma rays. Now the higher the frequency, the more energy that the wave has. Okay? Over on the right side you have radio waves. Those are long. They can be a meter, they could even be a mile long. Those are not the waves that come out of your radio. Those are the waves that go into your radio from a transmitter somewhere. This is the way everybody received radio in the olden days, and it goes into your radio, and those are called radio waves. They're very long, they're very low frequency waves. And then you can see as you move in the more energetic direction of the higher frequencies, you get microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Now you notice of that entire spectrum, all of those different types of waves and wavelengths and frequencies, there's only a very small part of it that's actually visible light that we can see. That's because it's only that range of frequencies that stimulates the nerves in the back of our eyes that causes them to send a signal to our brain. We won't get into the biochemistry of how that works. It's just, you just kind of accept that it is. So your eye is being hit by infrared, by ultraviolet, by X-rays, by gamma rays, by radio waves all the time. Not a lot of gamma rays, okay, or X-rays, but some of the lower ones, certainly radio waves. But they don't stimulate the nerves in your eye to send any signal to your brain to create any sensation of light or anything else. It's only that little small wedge right there in the middle, and they expand it out down below. So what you'll notice about visible light, we said over on the right side is the lowest energy. See up at the very top it says energy increases as you go from right to left. So radio waves are the least energetic, gamma rays are the most energetic. So if you go down to that light spectrum down at the very bottom, you'll see that what's happening is that red over on the right is the least energetic, has the least energy of any light wave. And over on the right, it's what would be called violet, kind of a purplish color. And that's on the left. Those are the ones with the most energy because they have higher frequency. So it is... it's the frequency of the wave of an electromagnetic wave that determines how much energy it has. And you'll notice down at the bottom, at the very bottom there, it says 7 times 10 to the 14th hertz, 4 times 10 to the 14th hertz. That's the range of frequencies that visible light is in. It's in between those two. Outside of those ranges, you have electromagnetic waves, but you don't have light that you can see. All right, so we'll be kind of referring to this as we go along through this year. Okay, so I'll continue. All electromagnetic waves travel at the speed of light, and that's 3 times 10 to the 8th meters per second. If we're going to be very exacting, it's 2.998 meters per second in a vacuum. A vacuum is a place where nothing exists, not even air. The speed of light is represented by a lowercase letter c. The speed of an electromagnetic wave is given by the electromagnetic wave speed equation. And there it is. Now this is an equation you might kind of recognize from physics. It's the wave speed equation. It applies to any kind of wave, though, the wave speed equation in general. This one, though, is specifically for an electromagnetic wave. So the speed is always the same, 3 times 10 to the 8th meters per second. That's the c. That never changes. That's constant. But then you also, as you did in physics, to get the wave speed, you multiply the wavelength. That's that upside-down looking y that's called the Greek letter lambda, and the frequency, and that's symbolized by nu. Remember, in physics, that was an f, so it's lowercase f. Now we're calling it nu for frequency. It's the same exact thing. So what does that mean? If the speed is always going to be the same number, 3 times 10 to the 8th, then when you multiply frequency times wavelength, you always have to get 3 times 10 to the 8th meters per second. So what does that mean? It means if your wavelength goes down, gets smaller, then your frequency has to get larger. They have to be inversely related because they always have to multiply the 3 times 10 to the 8th. If your frequency gets lower or smaller number, then your wavelength has to get larger, or a longer number, or a longer wavelength. Okay, so those two, lambda and nu, always have to multiply to be 3 times 10 to the 8. So wavelength times frequency must always equal 3 times 10 to the 8. As one of these values gets larger, the other gets smaller. So here's an example. What is the wavelength of an X-ray with a frequency of 1.5 times 10 to the 17th? Well, usually when they give you a problem to figure out something, you have to have two numbers, at least two numbers to figure it out. Here they only gave you one number, 1.5 times 10 to the 17th. But by recognizing that it's an X-ray is an electromagnetic wave, that means you know the wave speed. C, it's going to be 3 times 10 to the 8 meters per second, the speed of light. And again, it's called the speed of light even when it applies to an electromagnetic wave that's not a light wave. You still refer to it as the speed of light. So there's the formula over there on the left. Speed of light, C, equals wavelength lambda times nu. And so you solve it for wavelength because that's what the question's asking for. So that gives you speed of light over frequency. 3 times 10 to the 8 over the frequency that they gave you, 1.5 times 10 to the 17th. And that's 2 times 10 to the minus 9 meters. Now, 10 to the minus 9 meters is 1/1 billionth of a meter, and that's called a nanometer. The prefix nano, if you check your prefixes on the one of the reference sheets that I gave you, nano means 1/1 billionth. So it's 2 1/billionths of a meter, and that's 2 nanometers. For light, they always express light waves in terms of nanometers, 10 to the minus 9th. Okay, so just remember that. If you came up with an answer that was 200 times 10 to the minus 7th or something, you would have to convert that minus 7th to a minus 9th. We'll practice some of those problems on the assignment, how you do that. It's a simple conversion to do. Okay, now here's the part that you probably didn't talk about in physics. You certainly didn't if you had physics from me. It's not part of the curriculum. But it's this strange concept that we talk about light as being a wave, but it can also be a particle. In other words, think of it like a little ball. It actually has a finite size. It's not some big long wave that's stretched out. And it's really hard kind of conceptually to understand that, to get your head wrapped around that. It was for me, and it even is for scientists. And you can't treat it as both at the same time, a particle and a wave, but there are times when you want to talk about the particle nature of light, that it's like a little ball rather than a big long wave, and that it has a discrete amount of energy in each of those little balls. So let's go ahead and read this. So light also has characteristics of an object. These objects are called quanta. Quanta of light are called photons. You may have heard that term before. So that's a little package, or little ball of light, or of any electromagnetic wave, but photons are specifically usually what's referred to with light. A photon has a definite amount of energy based on the frequency and wavelength of the light. Physicist Max Planck developed an equation for the amount of energy in a photon. Energy has a unit of measure of joules. Where have you seen that before? You see that everywhere in physics. Joules. We use joules for thermochemistry when we talk about enthalpy. Joules is used for the amount of energy you put into a baseball when you throw a baseball. It's used for electricity. It's used for everything. It is the standard measure of energy, and you can convert one form of energy to another. So we're using it here also. Okay, this equation is the Planck-Einstein equation. So here it is. It's the energy. The E represents the energy in one photon, and that equals a constant called Planck's constant. And you can see it's a very tiny number, 6.626 times 10 to the negative 34th. It's about the smallest constant there is in science. It's a very, very tiny number. And then, of course, there's nu there at the end. That's the frequency of the wave. So what this equation does is it does relate the frequency of a wave. In other words, it relates the wave characteristic of light with the particle characteristic. That is the E, the energy in one photon. So you relate waves to particles. It gives you kind of a bridge between those two concepts. So important, the energy of a wave and its associated photon is a function only of the wave frequency and not the amplitude. Let me explain why that's a little counterintuitive. If you went to the beach and you stood in the ocean up about knee deep, and a bunch of little waves came along and just, washed up against your leg, a whole lot of little waves came along real quickly, you know, you wouldn't feel much energy from them. It would just seem like, yeah, it's hardly anything hitting my leg. If all of a sudden a 15-foot wave came along, just one, and it just hit you, it would knock you over. All right, so you'd say, well, which has more energy? And you'd say, well, the 15-foot wave does because it's bigger. The little waves, even though a lot of them are hitting you, you'd say not very much energy is hitting me with all those little waves hitting my leg. With electromagnetic waves, it's reversed. It's the opposite. The energy of the wave is not the amplitude. It's not the height of the wave. The energy in the wave is the frequency. The higher the frequency, the higher the amount of energy in an electromagnetic wave. So in other words, you can't think of it the same way you think of an ocean wave. It's not the height of the wave, it's the energy. Well, what does the height of the wave mean then? It'll tell you the brightness of the light. But brightness is not energy, and that's kind of counterintuitive too. It kind of goes against what you would think. Okay, the height of the wave, or the brightness of light, is not what determines its energy. So if we go back down here to our electromagnetic spectrum, right there, we see down at the bottom that red light over on the right has less energy because it has a longer wavelength. It's further to the right on that spectrum, so it has a lower frequency and longer wavelength than blue light over on the left. So here's the question: which has more energy, a really bright red light or dim blue light? And you would think it's got to be the bright red light. It's brighter, that's more energy, but that's not true. It's the dim blue light, because blue has a higher frequency than red, and therefore it has higher energy. So what a bright red light means is that a lot of photons are hitting a point, but they're all very low energy photons. Whereas with the blue light, it may be fewer photons, but they're high energy, and so they have a higher energy. So it's the frequency. Just kind of pin this into your brain. It's the frequency, not the amplitude or height of the wave, that determines how much energy that it has. Okay, so there we go. All right, so important. Okay, so let's just do an example. This is really just a plug and chug. Some of these formulas look a little intimidating, but they're just plug and chug problems when you're given a problem with numbers here. Okay, so find the energy of a photon of red light with a frequency of 5 times 10 to the 14th hertz. Okay, so you know the frequency. Planck's constant is fixed, 6.626 times 10 to the negative 34th. You multiply those two together, and you get 3 times 10 to the negative 19th joules. A really, really tiny amount of energy for a single photon of red light. Something that couldn't even be measured. All right, now there's a way to switch that over. This equation shows you the relationship between the energy of a photon and the frequency. What about between the energy of a photon and the wavelength? Because we know there's a relationship between wavelength and frequency. Well, if you come down here, right here, it says the electromagnetic wave speed equation and the Planck equation can be combined. So if you take C equals lambda times nu and you solve it for nu, so nu equals C over lambda. Now you come over to the Planck Einstein equation and you plug in for nu, you plug in C over lambda. You end up with the energy of the photon equals Planck's constant times the speed of light, and those two multiplied together are always going to be some constant because they're both constants, over the wavelength. So you can either figure out the energy of a photon from the frequency, that's the equation up above, or from this equation right here in this box. Okay? So the last equation relates wavelength to energy. Example, what is the energy of a photon of blue light with a wavelength of 400 nanometers? Well, one thing you got to do is convert the nanometers into a scientific notation into meters, because that equation requires meters. So a nanometer is 10 to the minus 9th meter. So you see down there on the bottom of the equation, it's 400 times 10 to the negative 9th meters. Up on the top, you have Planck's constant and you have the speed of light. Those two numbers never change. And so you end up with the energy in the photon of 5 times 10 to the negative 19th joules. Okay, let's pause for a second and let's see where you are on the assignment. So far we're at the end of page 3, and you can answer all of the questions on pages 1, at page 2. You can answer 10 and 11 on page 2. You can answer 12 on page 3. And let's see. You can answer 13. You can answer 14. And you can answer 14A and B, that is. So that's 3. So all the way through page 3 with these equations, okay? 15 we're going to talk about, actually number 15 I'll talk about once I do the video for the solutions to this assignment, and it's to explain those 6 equations that you see up at the very beginning of the assignment. We'll talk about those on the assignment here. Alright, let's keep going. So we haven't gotten to number 16 on the assignment yet. Let's keep going on this. So matter can emit, that means give off, or absorb energy in whole number multiples of hv, of Planck's constant. So it could be 2hv, 3hv, 4hv, and so on. The idea that energy is released only in specific energy levels called quanta was observed in 3 ways. One is called blackbody radiation. Heat from a stove produced a specific color, red. That's something that Max Planck noticed himself, that only one color comes out of a stove. The photoelectric effect is that only certain energies can cause electrons to be released from a metal atom. That was discovered by Einstein, and he won the Nobel Prize for that. And then an excited gas, and that would be light produced from excited gas atoms such as neon or argon. And you've heard of neon lights. They're actually not just neon, they can be argon or krypton, other noble gases, and that does it as well. The quantitized energy levels in atoms can be called orbitals or shells. You knew that already. Electrons can only be at one of these energy levels. These are similar to steps on a ladder. You cannot stand in between steps. You must either be on a lower step or a higher step. Work function. The work function is the amount of energy required to remove an atom from an electron from an atom of a metal, specifically a metal. If the amount of energy put into an electron is greater than the work function, it will be in the form of kinetic motion energy that will eject the electron from the atom at higher speed. Now, this may sound familiar. It sounds a lot like ionization energy, and it is. It really is the same thing, except work function applies to metals. Ionization energy applies generally to gases. Now, we're not going to really deal with work function at all, but it's just a term that you might come across. All right, now let's talk about the spectrum that we were looking at down there at the bottom of this of these notes. White light is made up of all the colors of the light mixed together. When white light is passed through a prism, it is separated into each of the component colors of light. This produces a continuous spectrum like the one shown in figure XX. Well, that should have been figure 4. Okay, in figure 4, just the one over to the right. That's a continuous spectrum. It's the one you were looking at before. Now, that's when you have a lot of different atoms involved in producing the light. They're going to give you this continuous spectrum of all these different colors of light. However, what about if just one single type of element is involved? Then this produces a line spectrum such as the one shown in figure 4. It's actually figure 5, okay, so those got mixed a little. Each element produces a unique spectrum of light, and it's by analyzing light from distant stars that astronomers can determine what elements make up the star. The line spectrum for hydrogen has 4 lines at blue, violet, blue, green, and red. So that's the spectrum. That's kind of like the fingerprint. It tells you that's uniquely hydrogen that has that particular line spectrum. And every element has its own unique line spectrum that identifies it as that element. Okay, how is light and color made? And this to me is one of the more interesting subjects. Where does color come from? Well, when an electron falls from a higher energy orbital to a lower orbital, it gives off an electromagnetic wave. If the wavelength of that wave is between 350 nanometers and 750 nanometers, then the wave is visible light. Johann Balmer discovered the line spectrum for hydrogen shown in figure, and that actually should be Oh yeah, figure 6 down below. Okay, the Balmer series is important because it emits wavelengths that produce visible light from an electron falling to the second orbital from the 6th, 5th, 4th, and 3rd orbitals. So let's go down and look at it. So this is the spectrum. So each of these lines, 1, 2, 3, 4, 5, all the way up to infinity, as you can see, represent the orbitals in a hydrogen atom. So 1 is the first orbital. That's where the electron normally sits, right? Is in its first orbital. But it can be excited by giving it energy and jump up to the 2nd, 3rd, 4th, or 5th. Okay? Now, they discovered that if the electron falls from either the 3rd, 4th, 5th, or 6th orbital down to the 2nd orbital, then it's going to emit a wavelength of a certain wavelength, and that wavelength happens to be visible light. So you can see if it falls from the 3rd orbital down to the 2nd, you see a red arrow there. Well, think about that. That's the least amount of energy. If you drop a ball out of a 2nd-story window, it hits the ground with a certain amount of energy. If you drop the same ball out of the 6th-story window, it's going to fall with a lot more energy. So the longer the distance that electron falls, the more energy it has when it gets to the 2nd orbital. Okay, so red has the least energy, and we said that already. A wavelength of red light has less energy than a wavelength of violet light or blue light. So falling from the 3rd to the 2nd produces a wavelength that gives you, or a frequency that gives you red light. If you fall from the 4th to the 2nd, that's that kind of turquoise looking arrow. Actually, there could be, that's the 2nd line in the line spectrum. If it falls from the 5th down to the 2nd, that gives you blue light, and if it falls from the 6th down to the 2nd, that gives you violet light. And so that's how light is created. By however much energy it falls, that energy has to go somewhere. It has to be released. When you drop a ball out of a window, when it hits the ground, what happens? The energy is released. It can either go back into the ball and make it bounce. It can make sound energy come out of it. So sound is a form of energy. It can cause the dirt down below to kind of scatter. That's energy. So that energy is released. When an electron falls in a hydrogen atom and it gets to its final destination, in this case the 2nd orbital, that energy is going to be released, and it's going to be released in the form of visible light. So Balmer series is more interesting, but there's 2 other series, the Lyman series and the Paschen series. The Lyman series is falling down to the 1st orbital, and the Paschen series is falling down to the 3rd orbital. Okay? But generally the Balmer is the one you talk about the most because it produces light that we can actually see. We can't really see those Paschen or Lyman series wavelengths. They don't stimulate our eye. Okay, an equation for each of these wavelengths was developed by Johannes Rydberg to determine the wavelength of light that will be produced for the hydrogen spectrum. Rydberg's equation is, and there it is. It looks scary, but it's actually not that scary. It says the reciprocal of the wavelength, so sometimes you'll see this solved for the wavelength where they flip it, but it's the reciprocal 1 over the wavelength equals the Rydberg constant times 1 over n1 squared. n1 squared is the lower energy level, minus 1 over n2 squared. n2 is the higher energy level. So if it's falling from the 5th down to the 2nd, for example, n1 would be 2 and n2 would be 5. Okay? It's not a hard equation. You have to have a calculator because of that constant. So let's go ahead and just do a problem. It's not really that hard. What wavelength of light is produced when an electron falls from the 5th orbital of hydrogen to the 2nd? Okay, so we're trying to find the wavelength. Okay, so N2, which is where it started, the one it started from, is 5. So you put that in for N2. N1 is the 2nd orbital, so you put that in where the N1 goes. You square those numbers and you multiply them by the Rydberg constant. Now, the number you're going to come out when you do that is not the number you see there, 4.34 times 10 minus 7. That's the reciprocal of the wavelength. So all you have to do on your calculator is divide 1 by that number, or just flip it. Okay, just however you do that on your calculator, flip it over, and that will give you 4.34 times 10 to the negative 7th. Now, remember we said we express wavelengths of light in nanometers. That's 10 to the minus 9th. So all you have to do is do a simple conversion. 1 nanometer for every, 10 to the minus 9th nanometers for every 1 meter. Okay, and when you do that, you're going to end up with 434 times 10 to the minus 9th. 434 nanometers. All right. Anyway, you'll see an example, but just how to do that conversion. It's just a simple conversion. Okay. All right. By the way, that's a wavelength of blue light. 434. If you go back and look at the spectrum at the end of this these notes, you'll see that that's a wavelength of blue light. Okay. Bohr model of the atom. Niels Bohr came up with the concept that atoms have orbitals of particular energy levels. His formula for the energy in any hydrogen orbital is. So this is what the kind of the model of the atom we've been using throughout this course. It's the nucleus with the circles around it, first orbital, second orbital, third orbital. And so he came up with this equation. Again, it looks a little scary, but it's really not that scary. It's just a bunch of constants multiplied together. So it's Planck's constant times the speed of light times the Rydberg constant. And if you multiply those together, you end up with negative 2.18 times 10 to the negative 18 joules. And then you multiply that by 1 over whatever the orbital number you want to know is. If it's the third orbital, you put 1 over 3 squared. If it's the fifth orbital, you want to know how much energy is in that, or in an electron that's in that orbital. That's all this equation is telling you, very simply. All right, so here's an example. What is the energy of the second orbital of hydrogen? So you use that negative 2.18 times 10 to the minus 18 times 1 over 2 squared, which would be 1 over 4. Multiply that by a fourth, and you get negative 5.45 times 10 to the negative 8 joules. So again, that's how much energy an electron in the second orbital of hydrogen would have. That's all that equation is telling you. All right. So this means that an electron in the second orbital of hydrogen has negative 5.45 times 10 to the negative 8 joules. The negative sign means that an equivalent positive amount of energy is needed to remove this electron from the hydrogen atom. Remember, energy into a system is positive, like money into your bank account. An electron removed from the atom all the way is said to go to the infinite energy level. It's gone to infinity in terms of energy levels, okay? It's beyond the 5th, 6th, 7th, 8th, 9th, 10th. It's all the way out to infinity, and so that's said to have zero energy. The Bohr model only works for hydrogen, but it is important because it introduced the concept of orbitals and the specific energy levels that an electron could occupy, and the idea that an electron must receive exactly the right amount of energy to move to a higher orbital. Now, wave behavior matter. This is kind of an interesting concept. It says that not only do light waves have the characteristics of an object, of a particle, like a little ball, and we call that a photon, but an actual physical object, like a tennis ball, actually has characteristics of a wave. And in fact, it moves through space like a wave, like a transverse wave. So just as an electromagnetic energy wave behaves like a particle of matter, Louis de Broglie discovered that matter moves in a wave-like motion. When a soccer ball flies through the air or the Earth travels through space, they actually move as a transverse wave. Yeah, they move up and down and up and down and up and down, just like a transverse wave. The reason we don't see this is that for large objects, the wavelength is so short, 10 to the negative 30th to 10 to the negative 60th meters, that it cannot be seen. Now, the de Broglie equation for the wavelength of an object with mass is wavelength equals h, Planck's constant, over m, the mass. That's abbreviation that you had from physics for mass. Now, in this case, that's not new. That's velocity. It's the speed that it's going. It's the velocity in meters per second. So, again, simple example. These are really just plug-in the numbers problems. What is the wavelength of a 1 kilogram soccer ball kicked at 15 meters per second? So there you have the formula. So h is Planck's constant, 6.626 times 10 to the negative 34th. The mass, it says, is 1 kilogram. It has to be sure it's in kilograms. It can't be in grams. Okay? Usually physics equations, and this is physics, require that things be expressed in kilograms. And then the velocity is 15 meters per second. You do the math on that, and you come up with 4 times 10 to the negative 35th meters. So no electronic measurement instrument can measure a wavelength of 4 times 10 to the negative 35th meters, which is why you don't see this up and down movement as a soccer ball travels through the sky, through space. All right, Heisenberg uncertainty principle. Werner Heisenberg developed the idea that the velocity, speed, and location of an electron cannot be known at the same time. This is known as the Heisenberg uncertainty principle. So think about it. If a car is driving down the street, and let's say you have one of those police radar guns, you can point it at that car and take a picture of it at the same time and know exactly how fast the car is going and where it's located. You could just think no big deal about that. But Heisenberg said you can't know that for an electron. He says if you know its velocity, you can't know its position, and if you know its position, you can't know its exact velocity. And that's called the Heisenberg uncertainty principle. So the position location of an electron is denoted by the letter X. So delta X simply means the amount of error in your ability to locate where it is. It could be X, or it could be a little bit to the right of X, or a little bit to the left of X, or a little bit above, or a little bit below. It's some change in X, it's some distance. And notice it's not set as equal to something, it's set as greater than something. It's a minimum amount of uncertainty that you have. So example, what is the uncertainty of the position of an electron in a hydrogen atom with the following data? So the mass of an electron, and that is the mass of any electron, is 9.11 times 10 to the negative 31 kilograms. Let's say the velocity is 5 times 10 to the 6 meters per second. That's pretty typical. And the uncertainty of the velocity, you're just not sure exactly, is 1%, so 0.01. So you go ahead and the uncertainty for the velocity then is 0.01 times the velocity, and that gives you a delta V of 5 times 10 to the 4th. Okay, that gives you the uncertainty for the velocity. Now that you know that, you can figure out the uncertainty for where it is, the position, the X. And you plug that in and you end up with 1 times 10 to the minus 9th meters. That's 1 nanometer, 10 to the minus 9th meters. So the uncertainty of the position of an electron in a hydrogen atom, 1 times 10 to the minus 9th meters, is about the same size as the hydrogen atom itself. This means we have no idea where that electron is at any moment. Okay, so you can't know the exact position of an electron. All you can kind of know is where generally it might be. And a guy named Schroedinger came up with a theory and a set of equations that was able to describe that. So Schrodinger's equation. Heisenberg discovered that we can never really know the exact location of an electron. Erwin Schrödinger devised an equation to determine the probability that an electron will be in a specific location. So Schrödinger is dealing with probabilities. Where is it likely to be? If you can't know exactly where it is, then at least maybe we can know where is it more likely to be. And this is using statistical probabilities. Don't worry, you're not going to have to get into statistics, but it's what Schrödinger did. Schrödinger's equation produces the wave function, and that's called psi. Like that guy that did Gangnam Style, psi. Okay, when you square the wave function, this will produce the probability of the position of an electron in a specific location. So it's only giving you probabilities. So if you look over there on the right, that's the 1s orbital. That's the s orbital for hydrogen. And you can see it's really dark blue, really close to the nucleus. We're assuming the nucleus is where those axes come together. So it's really dark blue. So the electron is likely to be very close to the nucleus. It never goes into the nucleus, though. Why that happens, we're not going to talk about, but it just never does. But you can see as you get further away from the nucleus, there's fewer and fewer blue dots, which means it's less likely to be that far distance, those farther distances away from the nucleus. Okay. The math for this is advanced. You just need to understand Schrödinger's equation conceptually. Just be able to explain it in words what it's saying, and that's what we just did. The probability is shown visually in the electron density distribution. The electron density distribution for the hydrogen electron in the first orbital is shown in figure 7. The electron occupies a spherical ball shape. So let's look at that. The electron density distribution of the hydrogen electron psi squared, the wave function squared, gives the probability that the electron will be in a specific location. Darker blue means higher probability. Okay, so let me reread that sentence there. The electron occupies a spherical ball shape with the highest probability of finding it is near the nucleus. Further from the nucleus, there is a lower probability of finding the electron. For reasons we will not go into, there is zero probability that the electron will fall into the nucleus. I asked that question when I was studying this. If the nucleus is positive and the electron's negative, why don't they just get sucked together and get pulled together? The answer is they don't. And that's all you need. You do not need to have to explain why that is. Okay, both Schroedinger and Bohr's models predict the same energy levels. The difference is that Bohr believed that the electron traveled in a circular orbit around the nucleus, the kind of model that we've been using in this class since the beginning of the class, just these nice circular orbitals. Schroedinger correctly believed that the electron moves all around the nucleus similar to a fly in the room. Schrodinger's equation has been completely solved only for a hydrogen atom. Schrodinger's equation provides a set of wave functions of different energy levels called orbitals. So what do the orbitals and subshells look like? Each of the subshells have specific shapes no matter which n orbital they belong to, which orbital they belong to, first, second, third, fourth. The s orbitals, sphere. So the s orbitals are shaped like a sphere. So now what we're going to do is we're going to take these orbitals we've been talking about. The first row of the periodic table is the first orbital. The second row is the second. We're now going to start breaking them up into subshells or suborbitals. We're going to find out they have layers within them, and we're going to learn what those layers are here. So the s orbitals, sphere. The s orbitals at any, and don't worry about that any n, that's something that I deleted, an explanation of something. It just at any orbital level are spheres. These are not circles. The higher the n level, the farther the electrons are from the nucleus. Higher s orbitals also have areas where there is low electron density probability. These are called nodes. No more than 2 electrons can fit into each of the s orbitals. So we know that already. The first orbital can only hold 2 electrons. But same is true with the second s orbital. And we're going to see where these s orbitals are located on the periodic table. Which elements are the s orbitals and which ones have the higher orbitals. We'll talk about that. But here you'll notice you have a 1s, a 2s, and a 3s. The 1s looks like what we'd expect. The electron can get close to the nucleus. As you get further away, it's less probability of finding it. Notice the 2s, though, has something kind of unusual. It's dark close to the nucleus, and then it gets very light, and then it gets darker again. Those are actually, in other words, there's a higher probability of finding the electron in that outer dark ring you see under 2s than there is in that in that space in between where there's very few blue dots. And you notice that the 3s orbital has two of those kind of open spaces. It has, near the nucleus, it has a very dark blue area. Then it gets lighter, then it gets a little bit darker again, kind of like a ring. And then it gets lighter, and then it gets darker again, another ring. So these are nodes, so the electrons generally want to be where those darker areas are. P orbitals. Okay, so there's a second level. Once you get beyond the first orbital, which is hydrogen and helium, and you get down to the second row, which is lithium over to neon, now you've got a second part of the second orbital. We've always treated it like it was a second orbital that could hold 8 electrons. Well, that's true. The second orbital can hold 8 electrons, but it has 2 parts to it. The s part and the p part. And again, you're going to see the periodic table. In fact, I'm going to show you just in a second here where those are. So p orbitals, potato. That's my little mnemonic because if you look at them there, they kind of look like potatoes. Some people would say they look like dumbbells or balloons or bowling pins. But the p orbitals have 3 subshells that have been described as potatoes, dumbbells, or balloons. Each of these 3 subshells has 2 sides called lobes. There's a 90% chance of finding an electron in the lobe areas. The p subshells are named px, py, pz. and each one can hold 2 electrons. So think about that. You got 3 of those subshells, px, py, pz, and each one can hold 2. That's a total of 6 electrons. As a result, the p orbital can hold a total of 6 electrons. When you add the electrons that the 2s and 2p orbitals hold together, you get 8 electrons for the second period row of the periodic table. We've always said that the second row can hold 8. What we now know is that there's 2 different sub-energy levels that they can be held at, the s level and the p level. So example, how many electrons can fluorine hold and where are they located? So if you look at fluorine, it's the second element from the end on the second row. So it has 2 electrons in its 1s shell. That's the first orbital. Then it has 2 in its 2s shell, and then it has 5 more in its 2p shell. So fluorine has an atomic number of 9, so it has 9 electrons in its natural state. 2 of these are in the first orbital, 7 of these are in the second orbital, and 2 of them are in the s, and 5 are in the p. You're going to see some specific examples of this in a second. So let's go look at a periodic table that kind of lays this out before we go to the next point. Here it is right here. So look at that periodic table. You notice that it has 4 distinct regions. The first 2 columns are s orbitals. So the first 2 electrons in any row, let's take the 2s, the second orbital, since we're familiar with it and we talked about it a lot. The first 2 electrons, we've said that 8 electrons go in the second orbital. We've said that all along. But now we're saying that the first 2 go into what's called the s orbital. That's a spherical shaped orbital. And the last 6 go into a p orbital. It's one of those potato-shaped orbitals, okay? And so we no longer just dealing with this single circle that has 8 electrons in it, or up to 8 electrons in it. They don't all have 8. We're talking about, okay, now there's 2 different parts to this second row orbital. The s part, which has 2 electrons, and the p part, which has 6 more electrons, okay? Now you see that the d orbital is down there in the transition metals. So when you get down into rows 4 and below, you're going to start to deal with d orbitals, and that's one we're about to talk about. And the one we never talk about in this class is the f, but you can see it has a distinct place on the periodic table. And the orbitals always fill up in exactly the order of s, p, d, f. So you have to memorize that sequence, s, p, d, f. The s orbital fills up first in a particular row, then the p orbital, then the d orbital, and then finally the f orbital, if it even has an f orbital. Only the really lower elements have an f orbital. All right, so that's where these are located. So let me just zoom in here a little bit. Okay, so right here, I'm at the beginning of the second orbital. That would be lithium. So it has 1 electron. It has 2 electrons in its 1s orbital. Those are the first 2 down here. Those are not valence electrons. Now lithium, the valence orbital is the second orbital. So it has 1 electron in its 2s orbital. If you move over to the beryllium, the fourth element, it has 2 electrons in its 2s orbital. So now its 2s orbital is filled. The 2s orbital can only hold 2 electrons. Now we come over to the other side, and we get to boron. Boron is right here. It has 2 electrons in its first orbital, 1s. It has 2 electrons in its 2s, and now it has 1 in its 2p orbital. Next would be nitrogen. Excuse me, carbon. Carbon would be next, and it has 2 electrons in its 2p orbital. Next is oxygen. It has nitrogen. It has 3 electrons in its 2p orbital. So 2 electrons in its 2s and 3 in its 2p. Then you get to oxygen right here. It has 2 electrons in its 2s, and then it has 4 electrons in its 2p orbital. Finally, or not finally, but next you get to fluorine, 2 electrons in its 2s and 5 electrons in its 2p. And finally you get to the end of the row, that's neon. It has 2 electrons in its 2s and 6 electrons in its 2p, so the 2 orbital is all filled up, 2 in the 2s, 6 in the 2p, so you're at the end of the row. Okay? And again, all of those also had 2 electrons in their 1s orbital. So there's a 1s and a 2s orbital for the second row, and they overlap each other. The 1s is closer to the nucleus, the 2s is a little further out, as we saw in the picture up above. Okay, so let's go on back here. So again, take a look at those. So let's look at the orientation. Now each of those two look like potatoes are one orbital. So the px is one orbital. Even though it has two lobes, it has one orbital. The py, it's the one going along the y-axis, is one orbital, but it can hold two electrons. And the pz goes up and down the z-axis. It has two lobes, but it's a single orbital. So you can fit two electrons into each of those. The px can take two, the py can take two, the pz can take two. That's a total of 6 electrons. And when you put them all together, they look like what you see over here on the right. That's the same thing all put together. And remember, overlapping that is the 1s orbital and the 2s orbital. They don't show that here because it gets too crowded and too busy. But those orbitals are forming spheres right in the middle there of where all those orbitals are, where all those potatoes are. Okay? So all we're doing is we're taking the orbitals that we always knew had an orbital that we always knew had 8 electrons, the second row, the second orbital, and we're saying, okay, but it has 8 electrons, but 2 of them are in a little bit lower energy level called the S energy level, and 6 of them, up to 6 of them, are in the P energy level, which is a little bit higher energy level. All right? So we're just drilling down a little deeper into the structure of an atom now. All right, so the first orbital holds 2 electrons. Those are the black dots. Okay, there they are. They're not valence electrons. If you're dealing with a second row element, like anything from lithium to neon or fluorine or anything else, that first orbital is kind of irrelevant. It holds 2 electrons, but they don't do anything. Then the 2s orbital, that would be lithium and beryllium. Those are those elements. Those would hold 2 electrons, and anything beyond beryllium would hold 2 electrons. And then finally you have, so we're looking at fluorine here. Fluorine has 5 electrons. Count them. Go to your periodic table, and it's the 5th element over in the P elements. It's the 7th overall, but let's go ahead and take a look at it again. Where is fluorine? Right here. So fluorine is right here where I'm circling my cursor. So there's 1, 2, and then in the p orbital, let's just talk about the p, there's 1, 2, 3, 4, 5 just in the p orbital. Okay? Okay, so there we go. So we come down here, actually. There we go. Okay, so you see this fluorine has 1, 2, 3, 4, 5. One of them is not filled. And I'm going to make a comment about the electrons at each of these lobes, okay? It's not the way it totally appears here. I'll make that comment later on. So basically, there's your 9 electrons. 2 in the 1s, 2 in the 2s, and 5 in the 2p. And that's how the fluorine atom, which is number 9 on the periodic table, would fill up. Now let's go to the next orbital. These are the orbitals that transition metals have. Okay, so if you look at that valley, look at that periodic table we were just looking at, this is where the d orbitals are. They're the transition metals. So the d orbital has 5 subshells. Each subshell can hold 2 electrons for a total of up to 10 electrons in the d orbital. Okay, you should know these orbitals, okay? They're a little tricky at first, but you'll see that 3 of them are very much the same. The dyz, that's the one in the upper left, has 4 nodes, and they're in between the y and the z axis. If you look at that closely, it's a little hard to read, but you can see it. Okay, the dxy has 4 nodes, and they're in between the x and the y axis, and the dxz is 4 nodes, and they're in between the x and the z axis. Okay, so that's those. Now you got something called the dz squared. Again, these are not math equations, but they look like it. And that's the one with the donut. That's why I call the d orbital the donut orbital, because it has that donut in it. And so that's how you kind of remember that one. And then finally, there's another one that they decided for some reason to call a dx squared minus y squared. Again, this has nothing to do with math that you have to figure out. It's just a name. And that has 4 nodes, just like 3 of the other ones there do, but those go right along the X and Y axis. Okay, you notice they're not in between axes like the other ones are. They're right along the X and Y axis. So there's 5 orbitals here, and each one can hold 2 electrons. That's a total of 10 electrons can be held by a d orbital. So this is what I wanted to comment and want to make about the nodes. Don't assume that each node can hold an electron. That's not true. Look at the DYZ, the one in the upper left. It has 4 nodes, but it can only hold 2 electrons. The DXZ, the one down in the lower left, it has 4 nodes, but it can only hold 2 electrons. The DZ squared, the one in the middle, it's got 2 nodes plus the donut, but it can hold 2 electrons. So don't think that each node can hold an electron. That's not true. Just remember that each of these orbitals, somewhere within them, can hold 2 electrons. So that's a total of 10 electrons. And if we go back down to the periodic table here, if you look at the d orbital, that's the transition metals, there's 10 elements there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And remember, each one contributes a new electron. That's 10 electrons in the d orbital. Okay? All right. I'm going to wrap this part of the notes. I'm going to continue them on another video. I don't like videos to really go much more than an hour if they're notes and half hour if they're problem solutions. Okay, let's see. There we are. Okay, so I'm going to wrap this, and I'll do the rest of the notes. I'll have the solutions, the answers coming up later today, and we will continue then. Okay, so I'll see you on the next video.